Assalamualaikum warahmatullahi wabarakatuh. I am Harip Badar P. Bondi and I will be discussing the rectangular components of velocity and acceleration. Unlike rectilinear motion, which means that the object moves along a straight line, for curvilinear motion, the object simply does not follow a straight path. The path is a curve. This curved path could fall in a 2D plane or it could be three-dimensional. To study the curvilinear motion, we will start with the basic rectangular coordinate system, but we'll learn about the other coordinate systems later. So let's first put this curved path in an XYZ three-dimensional rectangular coordinate system. And at a certain time, the particle has reached this location, and again, this position can be represented by the position vector r, which can be written in Cartesian vector form as xi plus yj plus zk. And don't forget, the path represents a sequence of positions of the particle, and the position is a function of time, and the x, y, and z components of the position vector r represent the positions along the xy and directions xyz direction respectively, and they are all also functions of time. So after some time delta t, the particle has moved to a new position p prime, which can be represented by a new position vector r prime. And the change in position can be represented by this vector delta r, which equals to the new position r prime minus the old position r. And the velocity is again defined as the change in position over the change in time and becomes instantaneous velocity as the time interval approaches 0, and this becomes dr over dt. Note that if delta t is very small, then r prime and r almost fall on the same line, and this very small dr is perpendicular to the position vectors and therefore tangent to the path. So here is an important conclusion. The direction of the instantaneous velocity is always tangent to the curved path. And since r equals to xi plus yj plus zk in the rectangular coordinate system, the velocity is dr over dt, which is simply dx over dti plus dy over dtj plus dj dt over k, or x dot plus y dot j plus z dot k. The dots are specific for time derivatives. And also we can write the velocity vector and the velocity components, where here vx over vy and vz represent the velocity of the particle in the x, y, and z direction respectively. And once again, the velocity vector is always tangent to the path at any point. Similarly, for the acceleration, which is defined as dv over dt, or the second time derivative of the position, as we are already very familiar with, acceleration equals to dvx over dti plus dvy over dtj plus dvg dtk, or x double dot I plus y double dot j plus g double dot k. And here the double dots are specific for the second time derivative of a function, and it can also be written in Cartesian vector form as axi plus y ay j plus akz, and ax, ay, and az are the acceleration along the xyz directions respectively. These are known as acceleration components. Unlike the velocity vector, acceleration in general is not tangent or perpendicular to the curved path. We would talk more about that in later sections. Let's look at this example. The curved path this object follows is given. Its vertical position y at any given time is related to its horizontal position x. By this equation, that y equals to 1/4 times x to the 3/2 power. Also, the horizontal velocity vx as a function of time is also given. Vx equals to 8 times t. And we are asked to find the magnitudes of the object's velocity, acceleration, and distance from the origin at time equals to 2 seconds, So since Vx equals to dx over dt, we can use the Vx function to first find the horizontal position x as a function of time. Since Vx equals to dx over dt equals to 8 times time, through simple integration, we can get x, the horizontal position, equals to 4t squared. And since y is related to x through y equals to 1/4 times x to the 3/2 power, therefore y, the vertical position of as a function of time, is 2t to the 3rd power. And therefore, the position vector is xi plus yj, which is 4t squared I plus 2t to the 3rd power j. And from the differentiation, since v equals to dr over dt, the velocity vector equals to 8ti plus 6t2 squared j, and do the differentiation again, acceleration equals to the dv over dt equals to 8i plus 12tj. Therefore, at t equals to 2 seconds, we can evaluate the position vector, the velocity vector, and the acceleration vector. And we also know how to represent vectors. And also how to calculate the magnitude of the vectors. And these are the answers that we were asked to find.